I know this is the last talk, so bear with me. The first thing I will preface this with saying that this is really going to be a talk that's sort of focused on mathematics, and I know many people here are working in computer vision proper. So I think I'm going to sort of hand-wave over a lot of the theorems. But my real goal, the point that I'm going to try and make, I think is applicable to a wide variety of people working in computer vision. And it's sort of a high-level idea that, how maybe incorporating symmetry into computer vision problems is something that is worth thinking about. So, all right, without further ado, so this is work with Howell and David Rosen. Okay. So the rotation averaging problem is really one of the fundamental problems in classical computer vision. It's a really sort of intuitive and straightforward problem. The idea is you're given a graph, and on the edges of a graph, you have some noise-corrupted pairwise differences of rotations. So you have rotations on the edges, and Rij equals Ri inverse Rk, and the goal is essentially to back out what are those underlying rotations. So in this little graphic, the data that you're given is rotations that live on the edges of this graph, and you've got to find the rotations that live on the nodes. So that's what we're going to talk about. I know that this problem is a very abstract, sort of highly idealized, just highly idealized computer vision problem, but has applications to a wide variety of problems. So point cloud registration, structure for motion, structural chemistry is actually the big one, because oftentimes with chemical bonds, you can determine the relative angle between two atoms just by stereochemistry. But to back out the full geometry of the molecule of interest, you basically have to do some rotation averaging. Okay, so I will lead now with the contributions of our work, and then I will sort of go through the theorems, but if you're interested, we can talk offline. So, okay, so the big contributions here are, this method that we're going to develop is not a gradient descent based method. It's not based on local search. It works for essentially any loss function. That, I think, is the main contribution. And using some sort of natural noise models, we can prove that this algorithm is indeed optimal. It's empirically so, especially in the regime of very high noise, which is the regime that robotics tends to work in. It's parallelizable, and you can sort of determine runtime versus accuracy. Okay, so briefly, let's just sort of heuristically go through the idea behind the algorithm. So the real tool that sort of fundamental insight here, which I think actually has some applications in sort of covariant machine learning, but I'll get to that later, is, if you have a periodic function, you can always sort of use the Fourier decomposition to specify this function by basically a set of real numbers, so these CF10, or complex numbers, sorry. Now, for SO3, so this group of rotations, there is actually sort of an analogy of the SO2 Fourier transform. And this is called the Fourier transform on groups, or the non-abelian Fourier transform. And the key difference is that for the SO3 Fourier transform, the CK are basically promoted to be a set of matrices. So in order to specify a function on SO3, you really need matrices, not just scalar coefficients. So this theorem is sort of related to group theory and representation theory, but this is sort of the key idea behind this whole work. Okay, so again, more sort of heuristics. given a RAF or a rotation averaging instance and a loss function, you can essentially use the Fourier transform on groups to turn your rotation averaging problem into basically a matrix eigenvalue problem. So I will briefly go over this. Again, please forgive me. This is very hand-wavy, but okay. So heuristically, the idea is we have our general rotation averaging problem where this Dij can be anything that we want. Using the Fourier transform on groups, we can essentially write this problem basically adding another index, which is sort of the analogy of these Fourier expansion coefficients for the standard Fourier transform. Using just a little bit of algebra, you can essentially write this as a problem that is essentially reduces to a problem over different harmonics. So the L index here is sort of the analogy of the frequency in the Fourier transform. Again, a little bit more algebra, but once you sort of have the problem in this form, you can essentially write this problem as what is known in sort of spectral graph theory as sort of the scalar. It's called the rho Laplacian. It's not super important, but I think sort of the key thing here is that you're decomposing your problem over what are essentially harmonics. So there's a theorem, you can look it up, it's quite a few pages, but it's basically this matrix is symmetric and positive definite and has 2L plus 1 fold degeneracy, and so you can essentially diagonalize it. And the key thing is that if you can diagonalize this, that eigenvalue subspace basically corresponds to the minimum solution of that problem. So this is just sort of a recapitulation of what I just said. This is finding the solution of the individual frequency subproblem. And then using the inverse Fourier transform, you can basically go back from this expansion into actual rotations. Okay, so I know that's very high level, but I think the key point here is just so we can get some baselines, we'll introduce some sort of ideas about noise. So, all statistical models have epistemic noise and systemic noise. So epistemic noise is, sort of the noise that you don't know about. Systemic noise is the noise models that you assume. So like Gaussian noise is a common systemic noise model. But in robotics, in rotation averaging, there are really two actual noise models. So for systemic noise, it's sort of this analog of Gaussian noise called Landrian noise. And uniform noise is obviously like that epistemic noise where you just don't know anything, right? It sort of corresponds to, my sensor measurement just failed. So we compare our methods with sort of three baselines. So the spectral realization method is to be derived from our algorithm where you're using just one frequency harmonic. This Weisfeld is basically the Govindu method, which is sort of the gold standard. And then graduated non-convexity is another sort of attempt to make a non-convex problem convex. So data sets, there's sort of some standards that can illustrate the real issues of rotation averaging. So this sphere data set is the true optimum, and this local minima is what you get if you use sort of a local gradient descent. So SO3 averaging on the sphere data set I think just from sort of experimental robotics, the key thing is your sensor measurements. Failure can usually be in a regime of 0.2, and our method can get roughly a factor of 2 increase, so from 10 degrees to 5 degrees, which can be the difference between your robot picking up the mug versus, you gotta go to Costco to buy a new mug. Yeah, so this is, just some sort of high level benchmarks. Yeah, so the thing that I know that this talk kind of seems like a mathematician's talk, and I guess you could ask, like, well, why are you telling me about this? I'm, I do neural network stuff. But I think at a higher level, what we think of as 3x3, like what we think of as rotation matrices are a 3x3, what's known as a representation of a group. And in this work, the Fourier transform that we use is essentially an expansion over different representations of SO3. And really the high level idea is that by including these additional representations, you can derive algorithms that have sort of either better performance or faster than existing methods. So this is sort of analogous to what's seen in equivariant machine learning, where I don't know how many people are familiar. I would definitely recommend reading up on it. I think it's a really promising field, but the idea in equivariant machine learning is to sort of parameterize neural networks using symmetry constraints. Like, we know the world is basically, if I change my coordinate system, not changing the world. So that's sort of the idea. Again, thank you for listening, and if there's interest or you think I did something wrong about some theorem, please send me an email. We're really looking for collaborators who are interested. Well, we're really looking for A100s, but collaborators are also good. Okay, yeah, so that's it. And questions, comments, concerns? Thank you. Any questions?
Are you taking any equivariant design into your approach?